Welcome to 5.1. 5.1, we're moving away from regression lines to probability. Students that seem to have problems with probability, typically I find are overthinking it. If I asked you what's the odds of rolling a 1 on a 6-sided dice, what would you tell me? 1 out of 6. Because there's 6 possibilities and only one way you can throw over 1. Well, that's a probability. So don't let the formula scare you when you see it. So let's get on into it. Well, the first thing we're going to talk about is the law of large numbers. And this is what we have found, that the larger the sample, the closer we get to the true probability. I just opened a pop, not a beer. As you can guys see, Verner's. So in theory, if I rolled a dice 6 times, I should have 1 1, 1 2, 1 3, 1 4, 1 5, and 1 6, correct? In theory. And the probability for each one, well, that's 1 divided by 6, because 1 out of 6 gives me 0.167. So let's go to StatCrunch, and that's what this is telling us to do if you want to play along, is to how StatCrunch has a simulator for rolling the dice, which is nice because it takes quite a long time to roll the dice to get to like 1,000. So here's my StatCrunch, and I still didn't clear it from the last video. That's okay. So applets, simulation, dice rolling, numbers on the die, 6. Now, how many die am I rolling? 1. So I'm going to say I want to equal 2. So in other words, we're doing the probability of 2. How many times 2 appears? That's considered, every time a 2 appears, that's considered a success over how many times we roll the dice. All right. Now, if we want to stay consistent, we all use the same fixed seed. Don't have to, but you can. So I'm going to put in 1 2 2 4, and then I hit compute. All right. And I say 1 roll. Tells me I got a 5. Well, that's going to take me forever, 1 at a time. So let's do 5 runs. It's 1 plus 5 is 6, right? Oh, but I thought the probability is 1 out of 6 of me getting each one of those numbers. Excuse me. Well, I didn't get any 3s and 4s. So let's roll 5 more times. Well, I'm still not getting any 3s and 4s. Dang. Rolled dice now 11 times. Where's my 1 out of 6? That's theoretical. But here's what happens. Let's go ahead and crank it up and do 1,000. Didn't that go a lot quicker 1,000 times? Now look at it. See how those bars are almost all even? This is my proportion for rolling a 2. And I said that 1 out of 6 should have a proportion of 0.167. Huh. What we're displaying here is the law of large numbers. The more times I keep running this, the closer I get to the theoretical. Right now at 1,000 rolls, that 2 is pretty well close. All right. Let's do another 1,000. Went over a little bit, but look at how the bars are coming more and more even. Let's do another 1,000. Notice I'm almost there. 1,667, 0.168, 0.166. It's not changing much now, is it? It hasn't changed much since 1,000. It's bouncing a little bit by hundreds, but look how evenly dispersed each bar is, how many times that number appeared. I put in 2. All right. What if I want 3? Well, 3 is 0.1662. How about 4? 4 is a little higher, but still it's not very far off the theoretical, is it? Let's look at 6. 6 is my lowest one. But you're seeing that it's telling me the mean for all my rolls with a standard deviation. But look at that. This is the display of law of large numbers. The larger the sample, the closer we get to the true probability. All right. So the law of large numbers in a nutshell is, as the number of repetitions of probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. Think about that. Doesn't that sound like circular thought? The law of large numbers is telling you that the more times we roll the dice, depending what we're tracking, whether it's the 2, the 3, the 5, the closer we get to the infamous 0.167 or 16.7% of the time. And you've seen that with the simulation. Now there's a coin flipping one out there, and in theory, you should get 50-50 heads, right? Well, we can pull a coin out, start flipping it, every one of us. It takes a long time, where that simulation does it in seconds. So that lovely blue box is telling you the larger the sample size, in other words, the more times we do the experiment or roll the dice, flip the coin, whatever it is, we watch for how many times. It's called a success. In other words, what are we tracking? And the one we did, we were tracking the 2. So every time a 2 popped, that was considered success. So how many times the outcome that we were looking for appeared over the number of times that we rolled it, that's probability. All right. So random process, we've heard that. Scenarios where the outcome is of trial is unknown, which it should be. We have an idea what should happen. So the law of large numbers is very important, because that is the foundation of why we need sample sizes big enough, because this bleeds over into the statistical world. We have discovered it's approximately around 2,500 is our sample size, that we get the best probability. Anything after about 2,500, we find our probability numbers don't change much, just like the dice. Same thing happens there. once we get into that, when we're talking about against the entire population, we have a nice random sample, about 2,500 people, we've got to where the percentages come out not much changing. Kind of interesting, ain't it? But that's all based off of the law of large numbers. This is the reason why when you heard me talk with the linear regression, when I said, we didn't make the sniff test and the R is not bigger than the crit value. What it said, give me a bigger sample. A lot of times it comes down to, I don't have a good sample, give me more. And as you heard me say, 2,500 is our magical number. All right. Now, the law of averages, as it says, the non-existent law of averages, and it doesn't. I've heard my sports people say, and I've heard them on TV too, yeah, they're putting in such and such in baseball game. He's due. He's due what? That's a law of averages. For my females out there, think biology, as it says here. Think about the children. What's the odds of having a boy? It's 50-50. What's the odds of having a girl? 50-50. Well, as you tend to have more and more kids, does that change? No. The gender or sex of the previous child does not affect the gender or sex of the current child. So I've heard people say, they've got 2 boys and they want a girl. She's due to have a girl. No, she's not. But I've heard people say it. It's like, well, yeah, no, she's not. People play the lottery. This number's due to pop. It hasn't popped in a while. Yeah, no. That's the law of averages, and it isn't such a thing. It's something we think exists, but doesn't. All right, now, events versus sample probability. Well, think of having the 2 children. Identify the outcomes. Well, you could have 2 boys, 2 girls, girl first, then a boy, or boy first, then a girl. Because, there is an order. First child, second child. So we have 4 possibilities. All right. So determining the sample space, it's actually what I just did, I'll be honest. Because the outcomes of having kids is you either have a boy or a girl. Sample space is how do they match up with 2 and 2? So the identify of having 1 boy. Well, it's not bad to spot. And how do we write it? This is another thing. Because the next page, you see the P of E. That's not what we write. We would write what it is that we're looking for. Probability of 1 boy. Capital P stands for probability. But at the end of the semester, you're going to hate the letter P because we have a P hat, uppercase P, lowercase p. Yeah, we have multiple P's. I think we got stuck on that letter as statisticians. So probability of 1 boy. Well, boy's not 1 boy. Girl's not 1 boy. But girl-boy is, and boy-girl is. So define the event E as having 1 boy. Well, that would be girl-boy, boy-girl, right? If I'm doing it as a probability, Well, two, because I have two ways of getting one boy, but out of how many possible? Well, 1, 2, 3, 4. Or 1 out of 2, you really should reduce. Or 0.500, 3 places, please. Probability can be written as a fraction, because it's really, you heard me how I said it, 1 out of 2, 2 out of 4. It's actually stated as a ratio. Or we can do it as its percentage, because really, what are we going to do? We take the decimal when we interpret, we take the decimal and call it a percentage. So 50% chance of having one boy. Even if we had 2 kids, you have a 50% chance of having one. You've seen how I did it. We had 2 of them that fit the match. Either the boy comes first or the girl comes first. But 2 boys is not one boy. 2 girls is not one boy. But they're one of the possibilities or the sample space. So you hear me saying this, it's like, we could do this also with a tree. So we're going to be dealing with too high of things to do trees. So the rule of probabilities. 1, a probability can never be greater than 1 because 1 represents 100%. It also can't be less than 0. So probability has to come between 0 and 1. Also, this is an important one. When we're talking probabilities, we're talking a different table. Remember back when we were doing relative frequency and frequency, I told you there's going to be one more table that's going to look like a relative frequency? Oh, here it is. A probability model, all outcomes must equal 1. So a probability table has to equal 1, where a relative frequency table, think way back to chapter 2, doesn't. Relative frequency doesn't. It'll come out almost 1, but a probability table must be 1. Now, just so you know, if this was an in-person class, I am notorious about the M&M project. I have been doing the M&M project since 2009. And it started because I heard M&M state that 32% of all M&Ms were brown. And I opened up a pack of M&Ms and I found 3 brown. I felt gypped. Wasn't 1/3. 32% is about 1/3. Yeah, it wasn't 1/3. So what did I do? I bought another pack. We're talking regular size packs of M&Ms. And again, I didn't get 1/3 of them being brown. So since 2009, I have been feeding students M&Ms, the fun size packs. And I am pushing, as of now, as of 2024, I have fed students almost 30,000 M&Ms in fun size packs. Everybody keeps telling me I need to email or send this off to M&Ms that maybe they'll give me some free M&Ms. Especially since this last round of M&Ms I bought, I paid over $5 a pack for those fun size M&Ms. Ouch. So maybe the M&M project's about to come in. But I have learned a lot about M&Ms. As funny as that sounds, every so many years they change the percentage of how they manufacture M&Ms. Sometimes they retire colors, sometimes they bring them back. They used to have a purple M&M. They had retired it. Back in 87 or so, they retired red because of the red dye scare. Well, then they brought the red one back with a different red. The most latest color they added was the blue, believe it or not. So I have already started giving students M&Ms this semester, and what you're looking at on the screen is this semester's current total of M&Ms. All right. Now, do you remember how you did the frequency table? You took your frequencies and you summed them. So we need to sum up this column. And hold on here, I've already done it. There is 415 M&Ms there. So we're going to take each one and we're going to divide each piece the 63 divided by 415, 55 divided by 415, 60 divided by 415, and 93 divided by 415. All right, I've got it all typed now. Handy dandy calculator time. So 55 divided by 415 gives me 0.133. It's 0.1325, which causes it to round. 0.214. 0.152. 0.128. All I'm doing is keying this into the calculator. 0.145. And 0.224. Now, as of right now, this is a relative frequency table. Again, the difference between a relative frequency table and a probability table is those probabilities have to equal 1. So we now total those percentages to see if we got 1. Because if we do not, we have to fudge it. Not statisticians. All right, 224, 145, 128, 152. I'm double checking, make sure I keyed them in right. And 133. And guess what? I get 0.996. So that means I have to go back through and fudge that up. All right. So looking at that, rhyme of reason and how I fudge it. Well, which ones that I didn't round up? That's my first ones I'm going to change. And I didn't round this guy up. So I'm going to round him up 1. Now that one was rounded. Oh, I think I found my error. 55 divided by 415 is 133. I miskeyed this. So you guys probably sitting there screaming at me. So let's try this again. .133 plus 0.215. So what happens when I get to lecturing at the same time, because I would have noticed that I've got 2 55s. Ah, now if we total it, we come up with 1.001. That means I now have to fudge it down. Now, I pick one that I had to round, typically. And I usually go after the bigger ones because they're already swaying stuff. So, I didn't have to round the green, but if I remember correctly, I did have to round the yellow. Yes. So I take it back down one. I tend to go after the bigger ones first and ones that I've rounded. That's how I make the decision. Then I go through and double check and make sure it adds to 1. But we were at 1.001, so I just need to back it off by 1,000th. Now it is a probability table because the sum is 1. And that comes from the second rule. The sum of each individual probability. That's what this is trying to tell you. The P of event 1, well, that's the probability of brown plus the probability of yellow plus the probability of red. That's what the P of E sub 1, E sub 2, E sub 3, and so on. We don't write the E. We write the verbiage of what the probability is, right? So that is a probability table. You see what happened when it doesn't equal 1. We got to budget down. All right. Key concepts. Something is impossible, the event probability is 0. Something is a certainty, probability is 1. 100%, 0%. Again, closer to 1. In other words, the higher the percentage, the more likely it's to happen. Closer to 0, the less likely. Mathematicians got to love it. We got to spell things out sometimes. And if I'm going to interpret it, the event is the probability, means it's how many times out of 100. All right. Or in this case, it'd be out of 1,000 because 3 decimal took to 1,000. So the probability of getting brown is 133 out of 1,000 M&Ms. You hear me translate? When you leave it as a bare percentage, like 65, but we don't. We go what? 3 decimal places. So it's really out of 1,000. So right. Hopefully this is not too terrible for you. This is just getting you guys geared up. All right. All right. An unusual event is something that has a low probability. Well, in statistics, our threshold is 5%, 0.05. You're going to find that later on that can change, but odds are we typically have a rule of thumb, it's 5%. So in other words, if something is less than 5% odds, we say it's unusual. All right. We have certain cutoffs. When we get closer to chapter 9 and 10, you're going to find out where the 5% comes from. So, empirical approach. We have three theories of probability. One is the empirical approach, where that one is the frequency of the event over the number of trials. All right. The next one is classical method. Looky here, equally likely outcomes. Think your dice. Again, a number of ways an event can occur over the possible outcomes. Computing probabilities using the classical method would be the dice rolling. But empirical method is the M&Ms. We've already done both of those. Understand they're real close because when we actually calculate, there's no real difference. It's in the number of times of the event occurred over, but with the classical approach, we have a theoretical, like the dice, 1 out of 6. And what did you happen as we approached with the law of large numbers? Yeah, it got close to the theoretical. Where empirical is the brown is the M&Ms. And just so you know, right now, M&Ms, yeah, I have what they're saying for percentages, just so you know. Heaven forbid I not know my M&M statistics. They're saying they manufacture. Okay, I'll do it after. They're saying they're manufacturing 13% brown M&Ms, 14% yellow M&Ms, 13% red. Blue is supposed to be 24%. 16%. And green is 20%. What do you think? Look at that blue. We only got 13%, but they're saying, according to the website, 24%. The green's higher than what they're saying, but look at the yellow. That's the other one that's off. The yellow's way higher than what it should be. But those are true numbers. These are, we did this. These are the M&Ms we ate at River Valley. So those numbers will increase as I get this coming week. So maybe what will happen with law of large numbers, they should get closer to the supposed to be true value. But I'm betting M&M hasn't updated their website yet because that is based off 2023 manufacturing. They're not stating 2024. So again, they change their percentages every few years. They're still running off 2023. They could have changed it. They're not due to, but they could have changed it. But we'll see. We'll see if it changes, if it pans out a little higher. As of right now, we're nowhere near what they say they manufacture. And just so you know, when I started this over the brown M&Ms, I discovered that, yeah, no, what they said they were manufacturing was not what I was getting from students. Also, a little tidbit. Back when I started this M&M trial back in 2009, it's hard to believe, 15 years I've been feeding M&Ms. 15 years. The average of M&Ms for fun size pack was 21. 21 M&Ms. Prices went up. We're now averaging 15 M&Ms per fun size pack. Price of M&Ms have gone up because I was paying a little over $2. I was getting ouchy when it was 2 something, but most of the time I could get them on sale for $1.99 or. But now I'm paying. It's almost tripled in price. I paid $5.60 a bag this past week. So almost a third M&Ms down, tripled in price. There you go. There's your inflation big time. But I will continue to do the M&Ms just because students laugh about it. So let's talk empirical. Empirical is frequency of the event, or in other words, how many times we got the success over how many times did we do it. What we did for the M&Ms. The M&Ms was an empirical approach. Well, another fun, silly thing is pass the pigs. If anybody's ever seen that, it used to be you rolled a pig. It was a little plastic pig about so big, and you roll it. And if it landed on its snout, that was worth so many points. If it landed on its side, and they had all different names for it. But the points were based off of how the pig landed. Well, sadly, I've seen a new version of Pass the Pigs, and they now got little pictures of piggies on a die. Like, really? That took part of the fun out of it, rolling a plastic pig. So, I just now realized that cuts off like that. So a class of 52 students rolled a pig 3,939 times. And what they found was a side with no dot. Yeah, there's a little dot on one side. He's got like a spot. It's a spotted pig on one side and a plain pig on the other. Razorbacks, when they land on their back with their forward little leggies up. A trotter is when they land on their feet. A snouter is when they land on their nose. And a leaning jowler is when they land where they're leaning on the nose and front feet. You would think the snouter would be the harder one, but no, it's actually the leaning jowler because the weight of the body will pull it on over. But as you can see, what's the most prevalent is the no dot. So pause the video right now and create a probability table. Remember how we did it? You don't have to add it up. I already told you it's 3,939. So pause it, create the probability table, and then come back as I fill this out. All right. My handy dandy calculator. I'm hoping you guys are getting the same numbers I am. Well, if I could type. Nope, nope. Yeah, can't type. All right. And again, what do we have to do? All I did was I did all this division. My nose is now itching, sorry. 0.31, 341, 329, 195, 093, 0.35, and 0.008. Again, I came up with 1.001. So again, I'm coming up here and I'm going to take it off one of the bigger ones. I think that I rounded that one up. Yep, I did. So I was thinking that was the one that I rounded up. Well, now we're back to 1.001. All right. So now looking at this, let's answer some questions. It says using results, what's the probability model for the way the pan? So we built the probability table. There's A. Oh, my nose. Estimate the probability that a thrown pig lands on the sidewalk dot. Right? Well, that would be 0.328 or 32.8%. Again, when do we write it as a percentage versus a decimal? When we go to interpret it and we put it in sentence and word form, we use a percentage. When we're just writing an answer, we leave it as a decimal. Now, would it be unusual for a leaning jowler? Well, is it? Think back. I just told you. What's the cutoff? 0.05. So is 0.008 smaller than 0.05? And the answer is yes. Yes, it is unusual for the leaning jowler since it is less, since the probability, we'll get right, of 0.008 is less than, and I just got through telling you guys, if we do what? Put in sentence format, it needs to be in percentage format. And what I just do, put in decimal. But 0.008 is not 8%. It's 0.8. Remember, we only move the decimal twice. All right. Now, probability of classical, equally likely. That's the closest thing. That's the key, because guys, I could ask you on this approach, the difference between empirical and classical is the classical equally likely to happen. All right. So that's the reason why I've given you examples. And there is the big differences, because classical is the assumptions that 1 out of 6 on the dice. Assumption is. Where empirical is pure observation. Classical doesn't have to be performed, where empirical does. There is the biggies. That's how you tell the two apart. Now, I did tell you there was 3 probabilities, 3 theories. The third one is called the subjective. And that is based off of your personal opinion or personal expertise. That's a judgment call. That's like your sports fanatics that have been tracking people and they're making a predictive based off of their own judgment and expertise in the field. That is subjective probability. All right. An economist predicting a recession, 20% chance. Well, that is his expertise of tracking and knowing things. So that would be a subjective probability. He has no, except he's sitting here watching the trends and such. All right. Weather forecasters. That's subjective probability. Now you know why they're not right. They're looking at the trends and, okay, according to these data and these modelings, It should be subjective. All right. Ladies and gents, that is 5.1. Hopefully I didn't bore you too much. Let's get out of here and end the recording. Good night, all.